Okay, this video will discuss simplifying radicals containing variables using the product rule. Well, a square root is simplified when the radicand contains no perfect square factors other than 1. So, for example, we have the square root of 20. Well, the square root of 20, it's not simplified because the square root of 20 equals the square root of 4 times 5, and 4 is a perfect square. Okay, so to begin simplifying square roots, we notice the following pattern, right? Square root of 9 times 16 equals the square root of 144, which equals 12. We have the square root of 9 times the square root of 16 equals 3 times 4, which equals 12. Well, since both these expressions simplify to 12, we can write this. The square root of 9 times 16 equals the square root of 9 times the square root of 16. Well, this suggests the following product rule for square roots. If the square root of A and the square root of B are real numbers, then the square root of A times B equals the square root of A times the square root of B. So this is the product rule for square roots. Alright? So in other words, the square root of a product, it's equal to the product of the square roots. Alright, so to simplify, let's work through another problem here. Alright, so the square root of 45. Well, if we factor 45 so that one of its factors is a perfect square factor, we get this. So we're going to use the product rule. Alright, so now we're going to write it this way. The square root of 9 is 3, and then the square root of 5. It's just we're going to leave it as the square root of 5. Okay? So the notation 3 square root of 5, it means this. It just means 3 times the square root of 5. Since the radicand 5 has no perfect square factor other than 1, the expression is 3 square root of 5, which is in simplest form. Okay? Alright, I do want to make a special note though. A radical expression in simplest form, it does not mean a decimal approximation, alright? The simplest form of a radical expression, it's an exact form and it may still contain a radical, alright? So, for example, our square root of 45, okay? This is exact, alright? In decimal form, it's an approximation. Okay, so this is not exact. Alright? So I just want to make sure that you get that helpful hint. Okay, now let's quickly go over simplifying radicals using the quotient rule. Alright? Well, let's examine the square root of a quotient. The square root of 16/4. Alright, well this equals the square root of 4, okay, because 16 divided by 4 is 4, and the square root of 4 is 2. Alright, well also, the square root of 16 over the square root of 4 equals 4, right, on the numerator, because the square root of 16 is 4, square root of 4 is 2. 4 divided by 2 is 2. Alright? Well, since both expressions equal 2, we can write this. Okay? So this suggests the following quotient rule. If the square root of A and the square root of B are real numbers, and B is not 0, then we have the square root of A divided by B equals the square root of a divided by the square root of b. Alright? So in other words, the square root of a quotient, it's equal to the quotient of the square roots. Alright, so let's look at some examples. So we have the square root of 25 over 36. Okay? So we can say this equals the square root of 25 divided by the square root of 36. And the square root of 25 is 5. And the square root of 36 is 6. Okay? Alright, let's look at another example. How about the square root of 3/64, which we can write as the square root of 3 divided by the square root of 64. Okay? The square root of 3, we're just going to leave that as the square root of 3. And the square root of 64 is 8. We have a perfect square. Alright? So this is using the quotient rule to simplify. Let's do one more. How about the square root of 40 over 81? Okay? We know using the quotient rule this can be square root of 40 over square root of 81. Okay? So using the product rule, alright, we can write the square root of 81 as 9. And we can do 4, square root of 4 times the square root of 10 in the numerator. Okay, so this equals square root of 4 is 2. Square root of 10 isn't perfect, so we're going to leave it the way it is. And then that all goes over 9. Alright, recall that the square root of x, say to the 6th power, equals x to the 3rd power, alright? Because x to the 3rd power squared equals x 6th power. So if a variable radicand in a square root has an odd exponent, we write the exponential expression so that one factor is the greatest even power contained in the expression. Then we use the product rule to simplify, alright? So let's go through some examples, alright? We're going to simplify each radical in some of these examples that I'm going to go over, alright? So assume that all of the variables represent positive numbers, alright? So the first one is going to be the square root of x to the 5th power, alright? Well, this we can rewrite x to the 4th times x. So this equals the square root of x to the 4 equals x to the 2nd power, and then multiplied by the square root of x. Okay, so to rewrite this, sometimes it's easier to see it like this. Okay, because you're just multiplying. Okay. All right, let's go over another one. How about the square root of 8y to the 2nd power? All right. Well, this is 4 times 2 times y to the 2nd power. Okay. This equals square root of 4y to the 2nd power times 2. Okay. We put these together, okay, because 4 and y squared they're both perfect square factors. So we're going to group them under one radical, all right? So this is going to be 4y squared times square root of 2, okay? So this is going to equal, so the square root of 4y to the 2nd power equals 2y, and then the square root of 2, it just stays, because it's not perfect square, so it stays the square root of 2, all right? So this radical simplified is this. All right, so let's do a couple more. I'm going to clear this and get a clean screen here. All right, so let's do 45 over x to the 6th power. This equals the square root of 45 over the square root of x to the 6th. Okay, so let's do our product rule. 9 times 5 over, and then the square root of x to the 6th power, we know that right away is just x to the 3rd. Okay, so in the numerator, this we know is the square root of 9 times the square root of 5 over x to the 3rd, which the square root of 9 is 3, and the square root of 5 is not perfect, so we're going to leave it. Alright, so that's the square root of 45 over x to the 6th power simplifies to 3 times the square root of 5 over x to the 3rd power. Alright, one more. We'll do the square root of 5p to the 3rd over 9. This equals the square root of 5p to the 3rd over square root of 9. Alright, we know the square root of 9 is 3, so let's take care of that one first. So let's break this one out using our product rule. So we have p to the 2nd times 5p. We know that this is the perfect square, right? Over 3. So we are left with p square root of 5 over 3. Alright, so the product and quotient rules, they also apply to roots other than square roots. So for example, to simplify cube roots, we look for perfect cube factors of the radicand. Well, recall that 8 is a perfect cube since 2 to the 3rd power is 8, right? So therefore, to simplify the cube root of 48, we're going to factor 48 as 8 times 6. Okay? And so then we're going to use the product rule. We're going to rewrite the cubed root of 8 as 2, right, times so 2 times the cube root of 6 is in simplest form since the radicand 6 contains no perfect cube factors other than 1. Alright, let's look at a few more examples. Alright, so the cube root of 54, alright, is 3 times the cube root of 2 in simplified form. Okay, let's do another one. Cube root of 18. The number 18, well, it doesn't contain any perfect cube factors. So, this is as simplified as it gets. Alright, let's do another one. Cube root of 7/8 equals cube root of 7 over the cube root of 8. So this equals cube root of 7, and the cube root of 8 we know is 2. Okay, one more, then I'll let you go. 40 over 27. Well, the cube root of 27 is 3. There's that cube root of 8 again. This equals 2 times cube root of 5 over 3. Okay, well that concludes this video.